Before we really get into inequalities, we've got to talk about interval notation, which should be familiar for us from a previous course. You can use interval notation or inequality notation to talk about values on x-axes where solutions exist, or later when functions are defined, where their domain is. I like interval notation better than all of the other types of notations personally, so that's the one that I use the most. Some things to remember with interval notation is if you have an open circle on your graph, you would use a parentheses in an interval. For the textbook, the way that the book is written, you already kind of see it down here. It's not going to use open circles on a number line. You might see one on a graph if it's an actual hole in a graph, but it's going to keep using the parentheses on the graph itself for on my number line, which is kind of nice because you don't have to remember what that means anymore. And if you have a filled in circle on a graph or the number is included, you would use a bracket. So again, on our graphs, we're going to be using those brackets as well. You can kind of see here in this table all of these types of intervals, set builders, inequality notations, and graphs that you can have, any combinations. But there's some patterns here to notice. If it's an open interval, meaning that it is not included as an endpoint, you would have a parentheses here. You would not have an or equal to on the inequality, and you would have a parentheses, which used to be an open circle, on the number line as well. Do we see that? And then if it changes to a bracket, that means we are including that endpoint in our answer. It is or equal to that number, and it changes to a bracket. There's a whole bunch of combinations here. You can mix and match them all that you want. However, if it's going off to infinity, which means it's going off to the side of your number line for forever, it will always have a parentheses next to the infinity. Don't give it a bracket. Parentheses is a concept, not a number, so we're not actually ever going to reach it. If we're saying the entire number line is used for something in particular, from negative infinity to infinity, you would have called that all real numbers before, but in interval notation, we use both infinities. Notice again, parentheses. So let's just practice using interval notation here. So our interval notation, we're going to draw and graph each interval in set builder, express each interval in set builder notation and graph. So first of all, for set builder notation, we start with the squiggly bracket and we say x such that. That's what that beginning part is. And then you translate it into an inequality. What's the first number in this interval? -1. And since there's a parentheses around that, I'm going to use the less than symbol, not the less than or equal to. I'm going to put x in between, and then the next number is 4. But since that 4 has a bracket around it, I'm going to use the less than or equal to symbol to finish out the set builder notation. If you're like, that's a whole lot of symbols, Miss Quigley, you're right. I'm going to erase something for a second. This is just an inequality. Does that look familiar to us? Yeah. All that set builder does is it makes this a set of numbers given that we are working with x's such that they meet those qualifications. That's all the fancy stuff around it. It's just really mathematical vocabulary for talking about different sets. But on a graph, here's what it would look like. We say it begins with an open interval at -1, so we put a parentheses at -1, and it ends at 4 with a bracket. We're going to color everything else in between it in. That is the interval on this random x-axis, this random number line, from -4, not including -4, all the way to 4, but including 4. Before this class, you would have used an open circle, then a closed circle, but we're switching that to brackets and parentheses. Does that make sense? Cool. If we're doing set builder notation for 2.5, 4 with brackets, set builder notation would be x such that 2.5 is less than or equal to x, which is less than or equal to 4, close braces. Why did I choose 2 symbols with the lines underneath them here? Because it's brackets. So that's the or equal to. We are including those endpoints. And of course, if we're doing this on our graph, we would go from 2.5-ish to 4, coloring that number in. Now from -4 to infinity, we're actually going to graph first. I think it'll be helpful to see the graph. If we go from -4 with the parentheses all the way to infinity, that just means I'm going to color in this graph all the way to the end of the graph and continue going off screen. We're going from, that kind of looks like it's a, I'm going to make sure that looks like an actual arrow. There we go, that looks better. To write this one in set builder notation, it's really helpful to see it on a graph because this symbol right here, this arrow, is the direction of the inequality symbol you use. Meaning we would say x such that x is greater than -4. Do you see how this arrow and this symbol are going the same direction? It's easier to start with a graph when you have a one-sided inequality for set builder notation. So use the graph. I think it's very helpful. Any questions about graphing this on a number line and writing them in the different versions? That table is going to be very helpful for you as you're doing these problems. And then we get into some really interesting sets. Now we kind of talked about this at the very beginning of class. Intersections and unions, something, it's like that very first day of class and almost nobody remembered what it meant, and that's okay because we talked about it. When we're talking about an intersection between two sets, an intersection is simply the list of things that are common to both sets. In the Venn diagram, that's the part where they're sharing. In contrast, a union is a set of elements in either A or B with no repeats. So like literally everything in set A or in set B combined with no repeats. And the reason we want to go over that is because we can find the union and the intersection of two intervals. The way we're going to do that is we're going to graph each interval on the number lines and then literally see where they either overlap or the entire domain in which they are covering the graph. So for example, these are the same intervals. One is just going to be a union and it's going to be an intersection. If I'm doing 1, 4, and I'm going to use colors for this, that would be from 1 to 4. Do you agree? Do we follow that one? Okay. But if I switch and I do from 2, didn't switch colors, from 2 to 8, here's what 2 to 8 is going to look like. We've got a bracket at 2 and a bracket at 8, and we're including everything in between. I'm just going to copy paste this down because it's the same interval for both A and B. So I'm actually just going to copy while I have my colors out. I'm going to color these just so we can see. Okay, the first question, part A, wants me to find the intersection. That means I want to find where these colors overlap. Where do they start to overlap? At 2. Where do they stop overlapping? 4. Now I have to use the endpoints at those places, which means I would say we go from 2 to 4. But this time I'm using the symbol that we start overlapping with and the symbol that we stop overlapping with, even though they came from 2 sets to begin with. Do we see that difference? We've got the blue bracket and the pink parentheses. Uh-oh. My air server just died? Okay, I'm back.
No, look at the symbols are different. One
Yeah.
has an N and the other one's a U.
Correct.
So U would be all of it.
Yeah, the union is going to want all of the things that are either in either sets with no repeats. So we can see that our union of these sets begins at what number? -1. Where does our union end? At 8. And again, whatever symbol is coming the furthest is the symbol that you use. So we have a parentheses from the pink and a bracket from the blue ending out our union. So intersection is what overlaps. Union is literally everything in either A or B. Do you see the difference in those two things? And it's small, so we just have to pay attention of whether we're wanting the union or the intersection. I said those backwards. The intersection or the union. Now let's throw it back a little bit. The reason we went over set notation and this intervals is because we're going to want to graph the answers for a lot of these linear inequalities. We remember, hopefully, how to solve an inequality because it's literally like an equation, except for when we multiply or divide both sides of an inequality by a negative number, the symbol is reversed. So maybe put some emphasis over negative number. If you're multiplying or dividing by a negative number, you flip the sign. So we're going to solve these inequalities, and we're going to graph them so we can see what the solutions would all be. We treat it like it's a regular equation. So the first thing I would do here to solve for x is subtract 3 from both sides. What would be next?
Divide by -2 and flip the sign.
Very good. Okay, so we divide by -2, so my spidey senses go off and I flip that inequality sign. And I'm dividing by -2 on both sides. Voila, we have our solution set. We're saying any number x that is greater than or equal to -4 is a solution. What would that look like on a number line, you ask? Thank you for asking. Here's my number line. When you're drawing it for yourself, you don't have to be super accurate. So like, here's -4 on my number line. Yeah? What sort of symbol would I put at -4? Would it be a parentheses or would it be a bracket? Bracket. Now, which direction should I color in?
To the right.
To the right, because one, we're looking for numbers that are bigger than -4, which these numbers would be bigger. Plus, oops, if you match up the symbol, this arrow is going that way. This inequality sign looks like an arrow going that way. So the graph is actually very easy to write. Do we remember these things? Hopefully. Let's do it again. This time we have x's on both sides, so we do have to deal with both x's on both sides. To start to solve for x, I'm going to subtract x from both sides. We'd end up with -3x minus 4 greater than 5. What's the next step? That was the actual question. What's the next step? Move the 4, so we add 4 to both sides. What's the next step? Divide, but we're dividing by a negative number, so your spidey senses start tingling and we flip the sign. This time it's going to be x less than -3. We do want to graph this. And again, I'm not too picky on you graphing them on your paper. The number lines that show up on computers will be more robust. But here's -3 on my number line. Bracket or parentheses? Parentheses. And which direction am I going to color in? To the left, because we want numbers smaller than -3, and this direction is smaller. Plus, if we check out that arrow, this arrow is going the same direction as this inequality sign if this was an arrow. So it's a nice, helpful little hint there. Now that's almost too simple. Can I make it harder? It'll be a nice review for you in solving. What if our inequality also contains fractions? We're not going to turn it into a decimal because this decimal would be 0.3 repeated in the center, and like we don't want to round that. What did we do when we were solving equations with denominators? Yeah, least common denominator. What would be the least common denominator for these denominators? 12. So I'm going to multiply every single term in this parentheses, in this equation by 12. So that's 12 times x minus 3 over 4 greater than or equal to 12 times x minus 2 over 3 multiplied by 12 times 1 over 4. Don't do too much at first, because if you try to start distributing, you're going to make your life harder. The reason we multiply by the least common denominator is because now all of these fractions are going to disappear. What's 12 over 4?
3.
So this is 3 times x plus 3. Greater than or equal to, what's 12 divided by 3?
4.
4. So that's 4 times x minus 2. And then 12 divided by 4, we've already said, is 3. Look at that, no more fractions. This gets way easier to handle when the fractions are gone. We can take over from here. We would distribute the 3. We would distribute the 4. We would combine like terms. I suggest for you to always move x's to the left when you're using inequalities. It reduces some mistakes. So if we move these 4 x's to the left, I end up with negative 1x. I know that means I'm making my x's negative. I'm doing that on purpose. Subtract 9 from both sides, so I end up with negative x greater than or equal to negative 14. And I wish I had left myself just like a teeny bit more space, but it'll be fine. What am I dividing by?
Negative 1.
So what else do I have to do here?
Flip the sign.
We have to make sure we flip that sign. And just because it's not nearby, I'm going to write this down. We flipped our sign. Amazing. We draw ourselves a number line to visually see this answer. Again, I don't care where on this number line you put 14. It can be smack in the middle as long as it is 14. Bracket or parentheses?
Bracket.
Bracket. And then I'm coloring in which direction? Left, because we want numbers that are less than 14. Those numbers are less than 14. So really, we can treat these exactly like equations until the very end, where if you divide by a negative number, you flip the inequality sign, and then we graph because there's multiple solutions to this, not just one. It's a range of, or a domain of numbers. So what happens if you get some of those weird things? Just like you could have no solutions or all real numbers for equations, you can have the same thing for an inequality. An inequality is going to have no solution is if you eliminate the variables and you obtain, just like an equation, some sort of false statement. Is 0 greater than 1? No, that's a false statement. That's when you would have no solution, and that's when you would give me the empty set symbol. However, if you eliminate all the variables and you end up with a true statement, is 0 less than 1? Yeah, even though they're not equal to each other, don't care about that. It is less than 1. That's the true statement for all numbers, and that's when you would answer all real numbers. So it's not as easy with an equation, because like obviously an equation, it would have to be like 0 equals 0, 1 equals 0. Those are really easy to see the difference in. You actually have to think about the numbers and if they're greater or less than each other. So if we see this in practice, we would distribute 2x plus 8 greater than 2x plus 3. Subtract 2x from both sides. I end up with 8 greater than 3. Is 8 greater than 3?
Yes.
That's true, right? So if it's true, that's a true mathematical statement. Our answer is all real numbers. But what about this other one? For B, if I subtract x from both sides, I'm left with an inequality, that says 7 less than or equal to negative 2. 7 is not less than negative 2, right? So that is a false statement. And how do you write your answer here? Yeah, what is that called? The empty set. Very good. It means no solution. It's just a symbol, so you don't have to write as many words. That's all pretty simple, but what if we have some sort of compound inequality? Meaning, we can take inequalities that have the word and in between them. So you see how this right here says negative 3 less than 2x plus 1 and 2x plus 1 less than or equal to 3. These two things are exactly the same, yeah? One is greater than a number, one is less than a number. We can write it as this compound inequality where we have two sides, a two-sided inequality called a compound inequality. We can still solve compound inequalities very quickly. We're going to do kind of like the absolute value equations where we do solve something twice using the same steps. That's exactly what we're going to do, but we're going to work from the middle to the outside. We're going to isolate the x in the middle, not on the side. So for example, if we're trying to solve this compound inequality, and we were just thinking about this right here, to isolate the x, what would you do first? Get rid of the 1. How do you get rid of a 1? Great. We're just going to do that on all sides, which means we now have -4 less than 2x less than or equal to 2. I've just subtracted 1 kind of from the middle to the outside. One more step to isolate x. What is it? Divided by 2. But again, I'm going to do that not just to two sides, but all sides. So we end up with -2 less than x less than or equal to 1. That's our compound inequality solution. Now what does that look like on a number line? Well, we have two numbers to put on our number line this time. We have the number -2 and we have the number 1. A second ago I said I didn't care where numbers went. I still really don't care how far apart they are, but please make sure the smaller number is on the left and the larger number is on the right. What sort of symbol do I put at -2? A parentheses. What symbol do I put at 1? A bracket, and we color in between them because the x is in between those numbers. So this is the compound inequality where x is greater than -2 and less than or equal to 1. That word "and," I actually want us to really emphasize this for ourselves. This is happening when you see the word "and." And the reason it is important to know when it's an "and" versus another type of statement is when we especially get into solving inequalities with absolute values. Solving an absolute value inequality, you will still essentially solve it like it's an equation, except for a couple of things. Number one, if c, the number it's set equal to, is not a positive number, an absolute value cannot be. So if u is an algebraic expression and c is a positive number, these are the steps that you take. Number one, if you are working with a less than c, you're going to create our compound inequality that we just solved on the other page. So to help you remember that, you're going to misspell the word "less than." Here's how you're going to spell it. You're going to spell it like this: less than. Because less than symbols are your "and" statements. This is when you do your compound inequality. If you're solving an absolute value expression that is greater than c, you're actually going to do two separate ones like you were doing isolate, separate, solve. The way I want you to remember this is that they have the word "or" in between them because you have two separate ones. You're going to misspell the word "greater" because this is for your greater than symbols. You're going to spell it like this: greater. So greater than is your "ors." Less than is your "ands." One of them you solve a compound inequality. One of them you solve two separate inequalities. And it's valid if that's greater than or equal to, or less than or equal to as well. So let's see what this looks like in practice. We're going to solve this and we're going to graph it on a number line. What kind of inequality symbol do I have? Is this going to be an "and" or an "or" statement? And because we have a less than symbol, I used the wrong color. Because we have a less than symbol, this is a less than or an and statement. With my and statements, we're creating a compound inequality. What we solve is not only x minus 4, absolute value, x minus 4 less than 3, we also solve with the negative 3 less than on the other side. Where did the negative 3 come from? Great question. Just change the sign. Isolate, separate, solve, but the separate step's different. You're still making one positive, one negative. It's just all together. Okay? At this point, now that we have it written like this, we can get rid of those absolute value bars and we can just solve like normal. Yes. So this is where we started, right? But since this is an and statement, I know there needs to be a double-sided inequality. So I'm going to repeat the sign and then change the positivity of that number. So it was 3 over here. That's what they gave us. Boop, negative 3. Yes. Correct. Okay, but once it's in this double-sided inequality, we don't need the absolute value bars anymore. And we have one step till we're done. How did we solve the compound inequalities? We just do what we would do to solve for x, but on both sides. So we're going to plus 4 everywhere. This is 1 less than x less than 7. We solved the less than, the and statement, using a compound inequality. Graphically, our solution looks like this. 1 is smaller than 7, but since they're both no line underneath those symbols, we fill it in like that. Have I lost anybody? Okay. Can we try another one? Yeah, I see the head shakes. Okay. Whoa, lots going on here. Let's start first by isolating the absolute value bars. Because we know in our steps for solving absolute value equations, we have to isolate these absolute value bars before we do anything else. So how do I do that? What should I do first? The absolute value bars is kind of like jail. Can't go in it until you take care of business, right? Or can't come out of it until you take care of business, I guess is more to think about it. So not looking at anything I've highlighted yellow, what can we move to isolate the yellow stuff? We will eventually. The 7, how do we move that? Minus 7 on both sides. So we're going to subtract 7 on both sides. We end up with negative 20. Okay, cool. Are my absolute value bars isolated? No. Now what do I have to do?
Divide by negative 2.
And do what with the symbol? This is why we want to do this step first, because we might have to flip that symbol over to the opposite sign. This is no longer a greater than symbol. It is now a less than symbol, which means we are solving or going to solve a compound inequality for less than, because it's an and statement. If I started to write this down again, I am going to erase those absolute value bars. But what number do I put on the other side here? Negative 10. Once you have it in a compound inequality, quick erase of those bars, we're good to go. 2 steps to solve this. What are they? Move the 5 by subtracting, so that becomes, I'm going to keep showing my work here so you can see where these numbers are going. This is negative 15 less than or equal to 3x less than or equal to 5. What's left? Divided by 3. And I do divide all of the pieces by 3, which would be negative 5 less than or equal to x less than or equal to 5/3. Solve from the inside out. Now, if we're just going to graph this one, again, negative 5 is less than 5/3. So here's my negative 5. Here's my 5/3. What sort of symbol do I put around them?
I have mine here. That's why.
Brackets.
I did it over here. That's why I was.
Did we follow?
Yeah.
Isolate, still separate, but the separate step with inequalities is either becomes a compound inequality or two separates. Last example here. For this last one, it's written kind of different than the ones we started with. What's different here? What's already, oh, it is already isolated, yes, but is it on the side where we begin things? And we can do this backwards, but I truly recommend rewriting the equation where the absolute value bars are on the left side, which means we're gonna flip everything about this equation. So here's my absolute value bars. I still have to keep the orientation of the symbol open towards the absolute value bars and closed towards the number. See how that's the same orientation? I need to do this because reading it in this direction, my trick works for you. What symbol is this right here now? Greater than. This is going to be one of the or statements. Now, we haven't seen an example of this yet because we'd only been seeing and. But for my or statements, all that means for me is I'm going to actually follow the isolate, separate, solve steps from a regular equation. We separate this into 5 minus 2x greater than 7. And 5 minus 2x less than negative 7. So we separated. One stays exactly the same. The other, what changed? The sign and the 7. So we flip to the opposite sign. We flip to the opposite sign. The separate step. But then it's just two little mini equations that you can solve using the same steps. So first I subtract 5 from both sides. I'm just going to go ahead and subtract 5 from both sides over here as well. Then we divide by 2, negative 2, sorry. And we flip our symbol one more again. And we divide by negative 2, flipping our symbol one more time. And we have two mathematical statements. We're going to put the word or in between them, since this is a greater than question. On a graph, what this looks like, it's really not all that crazy, but since it's not an and statement, we should not have connecting sets. Here's my number -1, here's my number 6. Around -1, I want things that are less than -1. So I'm going to color this direction. And then I also have a separate one that is a possibility, or I can be bigger than 6. So your or statements are not going to combine together, but they're going to be two separate things on your number line. Do we see that difference between and or? So all of our and statements, we had sets that overlapped. It was our intersections. For our or statements, we have two separate intervals on our number line.